Welcome to the Berkman Klein Center's Spring Speaker Series. Every Wednesday, we gather top academics, industry experts, and tech professionals to share cutting-edge insights on AI, social media, and more. Today, we are thrilled to welcome Sayash Kapoor, a PhD candidate at Princeton and co-author of AI Snake Oil. His award-winning research focuses on the societal impact of AI, and so join us in exploring groundbreaking ideas and fostering innovation. Sayash?
Thank you so much for the introduction, and thank you so much for being here. I'm excited to talk about recent work that I've been doing with my collaborators at Princeton and elsewhere, in particular, Arvind Narayanan, who's a professor at Princeton. And over the next 40 to 45 minutes or so, I wanted to go over three topics where we've particularly been interested in understanding AI's impact. In particular, what we've been thinking about is how to collect the evidence that allows us to make decisions about using AI in the real world, whether it is in AI for scientific research, in legal practice, or more broadly to understand the misuse risks. So these are the three sort of broad areas that I'll be focusing on. Let's start with scientific research. So one of the main claims, or one of the main things we've seen was as AI has been broadly adopted throughout the sciences, is that fields across disciplines have started increasing their use of AI. For example, this is an excellent figure from the study by Eamon Duede and others that found that across these 20 disciplines, we have seen in total about a quadrupling of the use of AI from 2012 to 2022. And in particular, what's shocking is that this is actually before the rise or the development and release of ChatGPT. So even before we had the latest wave of generative AI applications, the use of AI across the scientific, across these scientific fields had been growing pretty quickly. And in particular, the sorts of scientific research that I'm talking about for the purposes of this talk is scientific research that relies on AI to make claims about the world. So there are these 4 steps involved. In the first, you have real world data that's collected based on what's happening in the world. Using the data, we create a model that allows us to study something about the world. So then once we have the model, we can claim certain things about the model, about how it works. And finally, we translate it back to the world itself. Finally, we translate it back to this claim about the world. And so in this context, this rapid adoption of AI poses like a lot of questions for researchers seeking to understand AI's impact. And a lot of my own past work has focused on trying to answer these questions. In particular, I think there are 2 types of risks when we see this type of rapid adoption occur across scientific research. The first is the risk of errors in individual studies that use these AI models. In particular, we can sort of try to think of all of the different changes that are required to the methodologies in any given field that's adopting AI, and see where those things change or differ compared to previous methodologies. This is one big reason why we've seen a number of different errors in the adoption of AI across these fields. So let's back up a little bit. How do we even tell if an AI system performs well, whether it is in scientific research or anywhere else? The main way we do that today is by using this paradigm known as the common test paradigm, where you have this common leaderboard, or you have like a leaderboard where one part of the data set is sort of held out, and you only train the AI system on the other part of the data set that is often known as the training data set. And the distinction between the training set and the test set is critical, because otherwise the AI system has access to the data on which it will later be evaluated. So this is a fundamental sort of a tenet of modern machine learning, where you only train the AI system on data that it won't be evaluated on, and you use a completely different type of data set. This error is also known as data leakage. So let's see a few examples. One example of data leakage is when there is no train test split at all. So if you're only using one data set both to train the AI model and then to evaluate its accuracy, you're essentially teaching to the test. Now, this is a textbook example of overfitting, or like something that has been known for decades within machine learning, but it's still surprisingly prevalent. So for example, this excellent review by Russ Polrak and others found that of the 100 papers in neuropsychiatry that used AI, around 45 of them had no separate train tests. Another example of data leakage is when the machine learning model uses features that are not legitimate for the task at hand. So for example, this wonderful paper by Philo et al. Found that in a previous paper that tried to predict whether a hospital patient would go on to get hypertension, 5 of the 6 most important features in the model were whether the patient had already been prescribed antihypertensive drugs by a doctor. Now, as you can imagine, this model does not really have much clinical utility, because if a patient has already been prescribed antihypertensive drugs, then it's no longer clear what we should do with this information in predicting whether the patient would go on to get hypertension. A third and final example of leakage that I'll talk about here is when models used for diagnosing COVID-19 using chest X-rays had all images of people with COVID come from adults, but all the negative examples, all the images of people, of chest X-rays of people without COVID actually came from children. So once again, in this case, the models were likely learning to distinguish between images of children or images of X-rays of children versus adults, rather than distinguishing between people who did have COVID versus people who didn't. And the number of examples here do show that there are these sort of specific studies that went wrong. In particular, in this case, Michael Roberts and others found in this wonderful paper in Nature Machine Intelligence that of the 62 papers they studied, 16 of them had this specific issue. But my collaborator Arvind and I wanted to sort of take a step back and to see how often this actually occurs in scientific disciplines. One of the main findings from our study that resulted were that leakage is widespread across sciences that use machine learning. In particular, we found over 600 papers that were affected in at least 30 different fields. And the real kicker was that each of these fields seemed to be independently rediscovering leakage. So it's not as if fields were able to communicate best practices or converse with each other about what to avoid. Every time a scientific field adopted machine learning, they sort of had to rediscover these insights, rediscover these errors from scratch. So in follow-up work, we tried to figure out ways to address leakage and address other errors in machine learning-based science. One of the things we were inspired by is standards for better reporting scientific results. So in particular, we found that in health research, we have organizations like the Equator Network that is basically a repository of over 500 different types of checklists that you might be able to use if you're carrying out any given type of health research. If you're trying to use AI for a specific type of clinical study, there's a checklist for that. If you're trying to run a randomized control trial, there's a checklist for that. And so we realized that there's nothing similar really for a lot of machine learning-based sciences. So we convened this group of researchers who work on machine learning-based science and have looked at reproducibility and its implications from many different disciplines, including social sciences, mathematics, computer science, economics, etc. And we came up with the reforms checklist, which is recommendations for machine learning-based science. It consists of 32 items across 8 different parts of a machine learning-based science project. And our aim is to at least make it easier to surface these considerations and surface these errors, whether it is for authors who are looking to do research, or referees who are evaluating research, or even journals who are trying to improve the reproducibility of the research published at those venues. All right, so this is the first sort of type of risk when we adopt AI in sciences. That is the risk of errors in individual studies. And to some extent, we have some solutions that we can think of adopting, things like checklists, better reproducibility practices at journals, incentivizing peer reviewers to look at reproducibility, and so on. But a much more problematic issue, and perhaps a much deeper issue that I think hasn't yet been addressed in this way, is that the epistemology of various scientific fields drastically lags behind the technical advances that we seem to be making with AI. So to think about this claim, I think this view of science is helpful, where, at the base level, you have individual scientific findings, where you're using modeling to make claims about the world, and then translating claims about these models to claims about the world. And of course, as we've seen with this previous line of research, it can be hard to make this type of claim correctly. And there are many places where errors can creep in. But one level above these individual findings are theories, scientific theories. Box's famous maxim goes, all models are wrong, but some models are useful. And it is precisely these models of the world, these theories about what happens in the real world that are important to be able to understand any individual fact or finding. And one level above this level of theories about the world are paradigms, where the entire development of theory depends on certain assumptions that are somewhat unspoken at the level of individual studies, but are held consistently throughout a specific scientific paradigm. And the concern with the adoption of AI is that faster progress at the lower levels of this scientific research tree, if you will, might actually lead to slower research or slower improvement or progress at the higher levels of the paradigms. So precisely because of the fact that we can use AI to get more mileage out of existing theories and existing paradigms, that might lead to the existing paradigms sort of stick around for a longer time period. It might prevent the development of paradigms and theories that move beyond the existing level at which we do research. And there are many historical analogies, many times when fields have sort of gotten stuck in a rut, even as they produced individual findings at an ever more increased pace. We've seen this with, for example, alchemists who developed lots of techniques for distillation and crystallization and so on. But yet, before modern chemistry, their interpretations were really sort of couched in this mystical language about the world. We've seen this with geology before plate tectonics. We've seen this with biology before evolution. And in fact, perhaps one of the most important examples can be astronomy before the Copernican revolution. And I think this is actually an example that's worth digging into a little bit more because of how it came about. So the earlier model of how to predict the location of objects in space relied on these epicycles. The image on the slide shows what this actually means. You had these ever more complicated rules. And it turns out that these rules for calculating where a certain planet would be, were actually extremely accurate. In fact, they were so accurate that modern planetariums still use this epicycle method to calculate the location of planets in space. But the reason we switched away from this cycle, the concept of the epicycle, the reason we switched towards the model of the universe with the sun and not the earth at its center, at the time at least, was not that predictive accuracy for these methods was higher, but rather because of Occam's razor, which found that a far simpler explanation for all of the objects in space could be determined with this new way of looking at the model of the universe. And so it's not accuracy alone that led to this consideration. We needed to fundamentally change our theories about how the world works. And I think this is precisely the sort of thing that AI does not give us today. It excels at producing the epicycles of modern scientific research, but does not give us a way to interrogate claims about the world, does not give us a way to improve and move past existing paradigms into newer ones that might be required. So this is one reason why I think the use of AI in scientific research comes with this risk. Now, people have also made a far less bold claim compared to AI being used to automate all of science, which is simply using AI to automate AI research itself. Compared to other scientific claims, like claims about automating all of science, AI research is actually a much smaller, in some sense, easier problem, because it enjoys frictionless reproducibility. In other words, most of the claims we are making when we are doing AI research are not claims about the real world, but rather they're claims about the models themselves. So the most tricky part of using AI in a lot of other sciences, which is translating claims about the models into claims about the world, actually does not exist for a lot of AI research. So indeed, it is possible that, at some point we can use AI to automate various aspects of AI research simply because of this relative ease in adopting AI. But at the same time, a lot of the current work that we're doing in this direction seems pretty misguided. And I'll show you a few examples of how. So this is a screenshot of Sakana AI's AI scientist launch. This was an AI agent that this company created. They claimed that this agent could autonomously carry out open-ended AI research. And notably, they released a number of papers that this agent had written from conception to the end. Now, this release got a lot of hype, but when you looked just a little bit deeper into how well this AI scientist worked, you found that there were many fundamental shortcomings. For example, this thread by Jimmy Koppel basically went into and read all of the various sort of specific claims Sakana made and found that the research papers released by Sakana were not reviewed for novelty. It also found that these papers often made very minor changes to existing papers and called them novel. And finally, the results from the paper were very unreliable. So it's not like you could reliably expect new research to be useful. And if you need to have verification or experts looking into every single output of the paper anyway, it's unclear how much of an advance Sakana really achieved. So in our lab, we wanted to benchmark how well AI can be used to automate smaller parts of the scientific progress or scientific research, even if not these sort of broader changes. So we introduced this benchmark called Core Bench. The tasks in this benchmark are actually much, much simpler than automating all of science or all of AI research, perhaps. So given a paper, primarily computational paper, and the accompanying code and data to reproduce the paper, the task that an AI agent was given was to actually carry out the reproduction. Now, automating reproducibility in this way is actually a prerequisite to doing novel scientific research or novel AI research, because any new research has to build on advances previously to sort of reproduce existing baselines. And researchers perhaps spend millions of person hours every year on carrying out this task. So in some sense, this is a much smaller component, much less ambitious. In another, it is still something that could save millions of person hours each year if you automate this specific task. And what we found is that even the best agents as of today don't score more than 40%. Now you can see these models getting better over time. And in fact, even if you can reproduce just 40% of papers, that could be a huge saver of time for lots of scientific tasks. But to argue on that basis that today's AI is soon automating all of science or even all of AI research is clearly premature. In fact, this is what I see as a rough roadmap for automating AI research. Right now, we are at the lowest levels of difficulty along this gradient. We have tools that can help retrieve, we have simple computational tools, but we don't yet have automated data analysis and error detection tools. And the sort of higher levels of difficulty on this task, things like executing on ideas independently, and perhaps even fully automating most or all of AI research, are far down the horizon. Okay, so this is sort of a view of how things that seem similar, that seem like all of them contribute to automation, actually tend to differ in difficulty quite a bit. And clearly, the impact of being able to automate retrieval is very, very different from being able to fully automate AI research. Let's now move on to a case study of legal applications where something similar actually holds true. We have a spectrum of applications that differ in difficulty, and also applications that are the most difficult to evaluate or automate are also the ones that would be most impactful. So moving on to legal applications, I'll consider three types of legal applications. This is all based on work I did with Peter Henderson and Arvind, both at Princeton. The first is applications that require information processing. So these can be applications such as summarization or translation, perhaps transcribing meetings, even tasks like e-discovery are examples of information processing. The second is tasks that require creativity, reasoning, perhaps a little bit of judgment from humans. So these can be tasks like preparing legal filings, research assistance on various tasks, as well as automated dispute resolution, especially in the case of easy to automate parts of legal applications. And finally, I'll look at AI that's used for predicting the future. So these include criminal risk prediction tools such as Compass, as well as predicting the outcomes of court decisions. So we've seen a number of applications all through the spectrum of legal applications. Let's start with the first one, which is information processing. So it is true that language models like ChatGPT can actually be used for many of these tasks. They can summarize text, they can translate between languages, transcribe, they can even help with e-discovery and so on. But one thing to note is that special purpose software, especially in the legal domain, has long been able to do these tasks well. So for example, here's an article from the New York Times back in 2011, where the potential for e-discovery was highlighted. What's new here with tools like LLMs is that in these cases, a single tool which can be instructed in English, in natural language, can perform most or all of these tasks. Now, where tools like this would be most helpful would be for lay people, but not really experts in a particular domain, who have actually a lot of purpose-built tools for information processing tasks. So these are more relevant to the average Joe, perhaps, compared to legal experts like judges or lawyers who have at their disposal an arsenal of tools. Now, of course, these tools will be adopted, but they won't lead to a sea change. They will be incremental rather than revolutionary. Even so, tools like language models still do have quite a bit, a long way to go in terms of being completely reliable. So for example, one of the major problems that blocks the use of these tools for a lot of information processing is hallucination. That is, language models often fabricate content, they make up content that's not in the source material. A rough intuition for why this happens is because language models generate text incrementally. So if there's an error in, let's say, the first sentence of the text, they might keep outputting text that is consistent, taking the error for granted. And they're also trained to sound convincing. And in their attempt to be more convincing, they sometimes lose out on factuality. So this is the first type of task where information processing tasks have seen the use of LLMs. They can be useful for lay people, but at the same time, this is not really a revolution when domain-specific tools already exist. This brings us to the second type of application, which is tasks involving creativity, reasoning, and judgment. These include things like preparing legal filings, research assistance, and so on. And compared to information processing, this is a task where if language models were useful and reliable, they could have a big impact on the future of the field. And indeed, there has been a lot of hype around the use of AI for these tasks, all the way back to the launch of GPT-4 by OpenAI, when OpenAI claimed that the model could pass the bar exam, scoring as much as the 90th percentile test taker. Another example is Do Not Pay, which claims to have built the world's first robot liar. In fact, the CEO of the company, Joshua Browder, claimed that the company would pay any lawyer who uses their service in the Supreme Court $1 million for doing so. But unfortunately, the reality does not match up to most of this hype. In the past few months, we've seen many examples of lawyers falling prey to hallucination. In fact, hallucination is actually much worse for this kind of open-ended task, where you have to generate legal filings that can take any shape, compared to much more specified tasks, such as the information processing tasks we discussed earlier. An expert in these cases has to sort of manually go back and check if each of the things outputted by the language model was correct. Now, again, in the last few months, we've seen claims such as LexisNexis's claim that AI for law is now hallucination-free. In fact, a number of legal tech companies have launched products with similar claims. But once again, when Stanford researchers evaluated LexisNexis and Westlaw products on simple legal questions based on specific legal texts, they found that in up to a third of the cases, and in at least a sixth of the cases, the outputs were hallucinated. Here's an example. So in some cases, we saw hallucination basically completely reversed the intentions of a specific case. In another, it sort of made up paragraphs entirely. And this is just a screenshot of 4 of these. I think they found over 200 such hallucinations when experts rated the outputs of LexisNexis and Westlaw products. A big question then for a lot of AI research is, will hallucinations be solved anytime soon? Now, of course, there are many ideas that make hallucinations less likely. In the case of the legal tech products that we just discussed, these come with specific citations that prompt the user to sort of check if the text accurately reflects the citations. But unfortunately, as of right now, a full solution that is sort of robust and reliable across domains is kind of like unlikely and not really foreseeable. So how do we tell if these tools are actually helpful? As we discussed earlier, we usually in the past AI research fields have used benchmarks. These are benchmarks where a part of the data is used to train models and another part is used to test them. And the models are judged on how well they can respond to these specific questions. Now, it turns out that for the latest wave of language models, even though these benchmarks are easy to use as evaluations, they actually don't really tell us too much about how well these products work. This is because of 3 reasons. The first is that language models are trained on huge amounts of data. But when you train a model on terabytes of data on the internet, it is quite likely that the train test split that we talked about earlier cannot actually be preserved for the data sets we're using as evaluations. In other words, it might be likely that the data set that we are using to test these models was already included in the training data for the model. And because these systems are proprietary, because the data sets aren't really released, researchers don't have a way of finding out if these original data sets were in fact included in the model's training data. And once this is the case, it's actually quite likely that we are getting an over-optimistic or exaggerated estimate of the accuracy of these models. A second issue is construct validity. That is, the questions that are used in typical benchmark evaluations, such as the bar exam for legal settings, don't actually reflect what tasks lawyers might want to solve using these models in the real world. In other words, it's not a lawyer's job to answer multiple choice questions all day. They're doing something very different. And so the assumptions we have when designing bar exam tests for humans actually fall flat when we're using those same examinations for evaluating AI. And the final issue is that small changes to how we evaluate these language models can actually lead to huge differences in the results of the evaluation. This is known as prompt sensitivity. So even if you, for example, change minor things like the order in which the subparts of the questions are asked, this can lead to large changes in how the model responds to these questions. And so taken together for all of these reasons, I think that it is far more helpful to involve domain experts in the evaluation of AI to create benchmarks as well as do real-world evaluations of lawyers actually trying to adopt AI systems, because domain experts have a much better handle on what skills are essential and how these models would be used in the real world, rather than relying on simple static benchmarks, which I think are not really useful. One example of such an evaluation I should mention is LegalBench. It was another benchmark created by the teams at Stanford, which involved a lot of other people. This evaluation also showed the limits such as prompt sensitivity, but at the very least, it improves the construct validity compared to evaluations like the bar exam. Okay, so this brings us to the third type of legal application, that is tasks involving predictions about the future. One of the most prominent examples of such a task in the last few years has been criminal risk prediction. So the slide shows a screenshot of this investigation by ProPublica that found that risk prediction algorithms in criminal justice can be biased against Black people. Now, what stood out to me from this investigation was not just the fact that there's a lot of bias in the false positive rate of the algorithm, but in fact, that the algorithm's accuracy in many cases is really, really low. So in the appendix for this news piece, Angwin and others mentioned that the accuracy of the system that was being used to make these predictions was actually around 65%. And a follow-up study found that the same accuracy can actually be achieved by lay people who are basically just judging candidates or defendants based on superficial characteristics. And in fact, even worse, it was no better than a two-variable formula that simply relied on the age of the defendant and the number of priors. So it turns out that this COMPASS algorithm, which was using 137 features about defendants, was actually no better than very simple formula that basically just used two features about them. And the key thing to keep in mind is that in domain after domain, in study after study, we found that it's really hard to make accurate predictions about individuals, especially when those decisions are used to make consequential decisions, especially when those predictions are used to make consequential decisions about people. We should be extremely wary of relying on these decisions. And, in this field and in many others, it's also surprising that an accuracy of around 64%, as in the case of COMPASS, is considered good enough to make these life-changing decisions about defendants. Keep in mind that guessing randomly whether a person would go on to recidivate or fail to show up for the trial has an accuracy of around 50%. So this is the first type of application in legal settings, where we're actually making predictions using AI and then relying on those predictions to make decisions. A second type of prediction is about the outcomes of court decisions. So for instance, on the slide, you can see a screenshot of such a recommendation where computers were could purportedly be used to predict judicial decisions. This is an example from 1963. So that's right. For over 60 years at this point, we have been trying to use computers to predict the outcomes of judicial decisions. How well have we done? It turns out we've done quite poorly. So a recent paper by Medvedeva et al. Looked at the entire line of research aimed at predicting the outcomes of court decisions. They found that in the vast majority of papers, there are severe errors. In some cases, the AI model is directly given access to the answer, which leads to an overestimate of performance. In others, the AI system is not really given the exact verdict, but is given the opinion that accompanies the verdict. Now, as you can imagine, predicting the outcome based on the opinion given alongside a verdict does not really count for much. And in fact, when researchers have tried to remove these errors and reevaluate AI, it turns out that AI isn't very good at making these predictions. So for example, this is a model called Jury that also tries to make predictions about judicial decisions. It only has an accuracy of 60%. Much like criminal risk prediction, it's not very much better than a coin flip. So this brings us to the end of this discussion on legal applications. As a quick recap, these are the three types of legal applications that we've seen: information processing, creativity, and predicting the future. The areas where there's most excitement about the use of AI is in tasks involving creativity and reasoning, as well as predictions about the future. But it turns out that these are precisely the tasks where evaluating AI is extremely hard. And as a result, either AI does not really work well at all, for example, in making predictions, or we fail to conduct good evaluations of AI. And this is where we need to do a lot more work as a community in improving the evaluations of AI. In contrast, when we have clarity on correct versus incorrect answers, such as in information processing tasks, it is reasonable to both use AI in these settings, as well as to evaluate AI systems better. But this is also the task where we already have many of the tools that generative AI is being sold as a solution for. And so we don't think it'll lead to a big revolution in how legal applications are used. So in contrast, when we don't have good evaluations, such as in creativity, reasoning, and prediction, that's also where AI would lead to a much bigger change to the legal profession. But unfortunately, the current state of evaluations does not really allow us to answer the question of how soon we'll get to that point. All right, so this brings me to the third and final part of my talk, which is looking at the evidence for misuse risks in AI systems. So one of the main concerns that has accompanied the use of or the release of generative AI models is that these models will soon be used for rampant misuse. Some of these concerns include things like using AI for cybersecurity risks, such as automatically finding vulnerabilities in critical infrastructure. Other misuse risks include disinformation, as well as biosecurity risks. For example, many researchers have claimed that advanced AI systems can be used to give individual rogue actors the ability to create bioweapons. So how do we assess if these risks are actually serious versus when should we think about these risks as perhaps being on a longer time horizon or not really serious at the current state of the technology? Let's dive into one such case study. So this is an example of Sayash et al. From MIT. This is a group that looked at the use of language models for democratizing the use of biotechnology risks. For example, the specific threat model they had in mind was an individual perhaps who's low researched currently, gaining the capabilities to build these pandemic-causing pathogens. And on this basis, the paper recommended that advanced AI models should not really be released. Policymakers should be considering ways to clamp down on the release of advanced AI. And I think this was a paper that was taken really seriously, both in research as well as in the media, where several outlets reported on the potential for AI to cause bioweapons and pandemics. But when Guha et al. At Stanford looked a bit more closely at the specific claims in the paper, they found that browsing Wikipedia can actually yield pointers to substantially similar information as the paper itself provided. In particular, they were able to get most of the specific facts that the MIT group found problematic simply by searching for these same things on Wikipedia. So this brings into discussion a very important point for how to analyze misuse risk, which is that when we are evaluating the risks of AI and the risks of releasing AI, we don't just need to look at the absolute level of risk. For example, it might indeed be true that AI can be used to give people information about how to create bioweapons. But we also need to investigate the marginal or the incremental risk of releasing AI technologies broadly. In this case, the analysis that would be needed to establish that language models and AI can be used for causing biosecurity risks is not just an evaluation of what language models can see, but also a comparison with what people could find out independently or perhaps without the existence of these powerful language models, maybe just by using the internet or browsing medical journals. And in the few months after these studies were released, RAND indeed conducted one such study where they focused very specifically on the marginal or the incremental risk of using AI in this situation. So this is the report that they published back in 2024, where they compared a group that has access to the internet against a group that had access to both LLMs and the internet. And the main conclusion was that biological weapon attack planning currently lies beyond the capability threshold of language models. And in particular, they found no significant difference in the viability of plans generated with or without LLM assistance, so long as the control group also had access to the internet. This is an example of how biosecurity risks of AI should be evaluated. We've seen similar concerns arise in cybersecurity, where lots of people have claimed that AI can be used to rapidly speed up the detection of cyber vulnerabilities, perhaps even in critical infrastructure. Now, if the concern is that AI could far outpace humans in finding these vulnerabilities, we actually lost that battle 3 decades ago when we developed fuzzing tools that can automatically look for vulnerabilities in code. But the surprising thing here is that fuzzing tools were actually being developed by the multi-billion-dollar cyber defense industry, as well as investments by the government. Now, why is that the case? It turns out that cyber defense industries have strong incentives to improve AI tools that can find vulnerabilities automatically, simply because those same tools can be used for defense as easily as they can be used for offense. So for example, for both open and closed models, we've soon seen that AI can be used to detect cyber vulnerabilities. These are both screenshots where I pasted in a recent vulnerability in an open source repo and found that both ChatGPT as well as Llama 2 could find that vulnerability. But we've seen also that AI, and including modern generative AI, has rapidly improved cyber defenses because defenders have access to the same tools. And most importantly, they have much deeper access to the systems that they're trying to defend. So they can use these tools at a much wider scale, much more quickly. Two examples are on the slide. The first is from Google, where they've used a security-focused version of their Palm language model on Google Cloud to protect their clients from cyber attacks. A second is from this project called OSS Fuzz, which uses fuzzing tools to scan open source repositories for cyber vulnerabilities. And they actually found that using language models improves the coverage of their testing quite dramatically. So these are some of the sort of main misuse risks of AI that we've seen a lot of discussion on. On the flip side, I also think there are certain misuse risks where we do have evidence that there is this marginal or incremental risk from the use of AI. One of the main examples is NCII, or non-consensual intimate imagery, where we've seen the release of open models like Stable Diffusion have led to a rapid increase in the creation and distribution of non-consensual images. And we do urgently need to think about what societal responses are mandated, how we can change policy, how we can change the incentives for the companies that create these products and also distribute them. And so I think this framework of thinking about the marginal or incremental risk is helpful precisely for this reason. It points out where our attention in dealing with the misuse risks of AI is more urgently needed, and what types of risks can perhaps need to be observed for sure, but perhaps appear sort of at a longer time frame or aren't currently evidenced by existing states of the technology. Okay, so this brings me to the end of my talk. The few key takeaways that I want to highlight are that first, good evaluation is really important to understand AI's societal impact. It's not just important to understand how well AI systems work, but rather also to understand when and where we can use AI productively, and perhaps when and what tasks are best not left without the use of AI at this point. A second is that AI could automate many routine tasks and perhaps speed up certain aspects of the legal and scientific research process. But that doesn't automatically mean that full automation is around the corner. In fact, AI researchers have a long history of being over-optimistic about the scope of tasks that the systems they're building can actually feasibly automate. On the flip side, to assess the misuse risks of AI, it's not just enough to show evidence that AI can be used for a certain misuse risk, but it's also important to understand what the marginal or the incremental risk of AI over and above existing technologies is when we are carrying out these evaluations. And in particular, I think this evaluation of marginal risk should guide our thinking, our policy interventions, as well as our research questions in dictating how the future course of technology, or what the future course of technology should be. And finally, I want to say that a lot of this evaluation has the necessity of domain expertise. Domain experts have a major role to play, whether it is legal or scientific research, or in the development of better benchmarks, or perhaps even in understanding the marginal risks of AI. So for example, legal experts are sorely needed in creating legal-oriented benchmarks. Scientific researchers are best suited to evaluating the impact of AI on their own field, and cybersecurity, biosecurity experts are needed in evaluating the misuse risks of AI. In other words, I think the questions around the societal impact of AI are too important to be left to AI researchers alone. And we definitely need to broaden the pool of expertise that is involved in building these evaluations. All right, I'll end there, and I'm looking forward to your questions.
Thank you for such an insightful presentation. Some of our questions here. Rohan asks, how do you see the evolution of benchmarks in the development of analytical AI tools? Given the cost of AI models, developers need to be able to sell their models to customers, and top performance on objective benchmarks is vital to that. So some level of teaching to the test is inevitable, but do you see development in overfitting resilient benchmarks?
Yeah, that's a fantastic question. So in a lot of our recent work, we actually have been thinking about how to develop benchmarks that can be robust to overfitting or leakage, as well as improve on construct validity. I think there are two sorts of solutions to the problem. The first is to build benchmarks privately. So we have seen a number of companies switch to not releasing the test sets for their benchmarks. In particular, Scale AI recently released the Seal series of benchmarks, which are completely private. The test set is never revealed. I don't think that's a foolproof solution simply because companies can evaluate various models, see how well they do on the leaderboard, and make tweaks or decisions based on the leaderboard accuracy. This is often called human in the loop overfitting. But I do think private leaderboards have a place in the future of evals. I think more broadly, one thing that we haven't seen enough of is studies within the actual firms that are adopting AI. So it's not enough to rely on these static benchmarks. It's very helpful to be able to understand what happens when workers are using AI to speed up their work on specific tasks, or to automate parts of it, or to augment certain tasks they're doing. And for that, I don't think benchmarks are the solution. I think things like uplift studies, figuring out how quickly AI is being adopted, even things like the revenue for companies that are building these tools are all much better indicators of how useful AI is compared to just relying on the benchmark results alone.
Thank you. And Jonathan asks, how will review work? The amount of claims already far exceed the community's capacity to review. How could AI help with the explosion of review needs in that they don't overconstrain longer term epistemic shifts?
Yeah, that is a fantastic question. I don't have a complete answer to this, but I do think there are certain things we can do to help. On the AI side, I do think it's helpful and productive to build tools that improve the current status of scientific reproducibility. In our own lab, we've been doing some of this work. We have been seeing this work from other groups as well. And I think the reason this is important is because no peer reviewer or most peer reviewers actually don't have the capacity to go into the code, run it, make sure it is reproducible, and evaluate if it works correctly and can be loaded. In some of the work where we found reproducibility errors, the error was in one line of code out of a 10,000 line code base. And the only reason we were able to find this error was because I worked on this code base for like 3 weeks. That is certainly not something we can expect of peer reviewers. And so in general, I think using AI to improve epistemic practices, using AI to improve reproducibility, I think is an interesting direction that we should definitely invest in. That said, there are certain things that we can do. So for example, encouraging researchers to provide the data and the code that they use to create the results is a non-AI intervention. And if there's like a paper that's simply out there is not getting much attention, maybe no one will make the effort to investigate if it's correct. But on the flip side, if a paper is being cited, is getting attention, people are trying to build on top of it, then this code and data becomes extremely helpful. There's this saying that goes, many eyes make shallow bugs. And so the more attention a paper gets, the easier it is to spot issues, errors, and bugs. And I think for doing that, it's essential that journals and scientific institutions incentivize reproducibility practices.
And what strategies can be used to regulate open source generative AI?
Yeah, that's a great question on the misuse potential for open source AI. I think crucially, perhaps the reason that the question is about open source models, or perhaps even open weight models, which are where the model weights are released openly, is because once the model weights are released, there is no taking them back. Unlike API-based models where OpenAI provides the API to say GPT-4o, OpenAI can actually rescind access to specific users or even the entire model if specific misuse risks are later realized. But this is not the case for open source or open weight models, where developers have very little control. These models can be uploaded to peer-to-peer sharing websites and be distributed without any control over how the model is used. So it's an interesting question about how we should think about regulating open source models. I think for many of the misuse risks that I pointed out here, the best defense, in my opinion, actually lies downstream of the specific model itself. So for example, when it comes to biosecurity risks, with or without AI, I think biosecurity is best achieved at the material synthesis and screening layer. So today we have tabletop DNA synthesis tools that can be used for creating like different forms of nucleic acids. We don't really have good mechanisms, at least right now, to screen what these tools are being used for. In the future, I hope and think that the best way is to restrict access to who gets access to this hardware, as well as to restrict what like materials can be synthesized, perhaps even using AI to filter out potentially harmful substances. So that's for biosecurity. Similarly, for cyber defense, I think the best defense is incorporating AI in all critical infrastructure to proactively find vulnerabilities and bugs. I think that will go much further than simply regulating the use of these models. Because if you think about it, finding cybersecurity bugs is not actually an offensive activity. It can be either used by offenders to sort of find and exploit bugs, but it can also be used by defenders to patch bugs and to patch them before the products are released or before they can be exploited. And so in some sense, restricting the ability of these models to find vulnerabilities would kneecap their ability also to be used as defensive tools. So for that reason, I think the best defense is in incorporating these models to find these vulnerabilities and improve cybersecurity, rather than in simply restricting access or regulating at the model level.
And Jessica asks, to what extent do you think these issues related to evaluation and evidence collection are a result of incentive structures within the AI/ML research community, both in academia and the private sector?
Yeah, I think the incentive structures have a big role to play here. So especially in academia, I think things actually might even be a tad bit worse than in many industry applications. Because for academics, the final output of a research project when you're using AI is the publication of a paper. It is not a technical artifact that people actually use on a day-to-day basis. So unlike in the industry, when you find a bug in a system, you can actually go back and fix it. For academia, I think many of these issues are really hard to correct. We found this with our own work in reproducibility, where many of the authors of the papers where we found errors were quite reluctant to acknowledge and fix the errors in their paper. And I think the incentive structures for publishing more such papers are also not in the right place, simply because reproductions of existing work are not really valued as much as novel research. And so for all of those reasons, academia is pretty hostile to improving reproducibility. Of course, there are small steps being taken. And overall, in the long term, I'm optimistic about us getting there. But in the short to medium term, I don't think academia is in a good place. In fact, I think things will get a lot worse before they get better. When it comes to the industry, of course, there are the incentives of selling the models to end users and customers. And I think those are pretty hard to get around. But at the same time, there are other reasons why evaluations are hard beyond just incentives. So for instance, the issues around construct validity generally do require domain expertise. They generally, solving construct validity generally requires hiring people or contracting people who have expertise in a given field to spend hours, days, or months of their time coming up with new benchmarks. And that is a cultural shift that the AI community has not yet had to experience before. For much of its history, AI could rely on basically like detached benchmarks. You have things like the iris benchmark, where you're predicting what a given flower is based on the petal and sepal shape. No one really cares about flowers in the AI community. What they care about is the accuracy of the classifiers. And so in this detached way, when AI was operating in this detached mode, it had this frictionless reproducibility that I think we're starting to see kind of fall short once these systems are becoming useful enough to being incorporated into a large number of products. So I do think a part of it definitely is the incentives, but another big chunk is this cultural shift and the need for domain expertise and just the problem being genuinely hard in the first place.
Well, Tanya thanks you for a very interesting presentation and asks if you could please tell us whether you see parallels between the issue with using AI in scientific research and in legal applications, or do the issues also differ in certain respects?
Thanks. Yeah. So I think the issues are similar to the extent that there is like a gradient of applications. Applications that are less consequential also turn out to be easier to evaluate, whereas applications requiring more nuanced implementations or going after more ambitious things are also harder to evaluate. I think beyond that, there are a few differences, though. The first is, unlike scientific research, the legal profession has its own set of norms where the expert or the practitioner is accountable to someone at the other end. Of course, scientific researchers are accountable at the end to their funders or to the scientific community or their peers, but there isn't this one-to-one correspondence in the specific customer that you have at the end of the day. I think for that reason, we've already seen the development of many AI tools and applications, such as things for information processing like transcription, translation, e-discovery, and so on, that were evaluated pretty well and that have proven useful to incorporate into scientists or into lawyers or workflows. In contrast, I don't think we have really explored the breadth of scientific research tools that we could have come up with, even given the existing capabilities of AI systems. That is changing as AI researchers turn towards science as a domain where they can sort of show off the expertise of AI models. I think we have seen investment into building these tools, but it's surprising to me that even simpler tools on the spectrum that I described for scientific research aren't yet very well developed, as opposed to legal research, where you have a healthy functioning market, a big legal tech market that sort of goes after these problems and has solved them successfully in many cases.
And our final question, what do you see as the future of evaluation in this space, especially given the inherent limited scope of static datasets?
Yeah, that's another fantastic question. So I think if you think about the types of evaluations we've talked about in this talk, on one end of the spectrum, we have static benchmarks, right? So we have benchmarks that might poorly reflect like the state of any particular field, things like the bar exam for figuring out if a model can do legal reasoning. I think static benchmarks will improve drastically. So we have seen how impactful these benchmarks could be, for example, in domains like coding, where as opposed to the earlier generation of coding benchmarks, things like human eval, which were really basic coding problems, in the last couple of years, we've seen a number of benchmarks that are much more involved. For example, SWE-bench tests the ability of language models to generate solutions to GitHub issues. These are real world issues that are supposed to toy problems like in human eval. And I think we'll continue to get better at that. On the other end of the spectrum are downstream applications. So these are evaluations that might be done through uplift studies or through surveys of users, or perhaps by looking at the impact of introducing a tool into a workplace. And once again, I think we haven't yet paid too much attention to how AI is being adopted across institutions, but I think we'll continue to see more of it. And I think alongside both of these, we are starting to see this third sort of sphere of evaluation, which we like to call midstream evals. So these aren't really upstream in the sense that, they're not really about issues that are detached from the real world. They aren't really downstream because we aren't evaluating how well AI systems work, but rather the key distinguishing feature is that you have evaluations that sort of compare these agents or bench or language models on like a vast number of different applications. So you might have multidimensional applications or evaluations that test how well agents or language models do at legal tasks, as well as software engineering, as well as web automation, as well as scientific research, and so on, that are conducted by these third parties that aren't the industry and aren't the downstream providers. and I think have a lot more credibility as well as standardization in coming up with this type of eval. So 2 examples that come to mind are HELM, which is a Stanford University project. HELM stands for Holistic Evaluations of Language Models, where they compare, I think, over 40 different models on over a dozen different benchmarks, and they try to evaluate how well these models are across the board. Second example is the Open LLM Leaderboard by Hugging Face, which again does something similar, but strictly for open models. And I think we'll continue to see more innovation here for coming up with these standards and conducting these third-party evaluations.
Well, Sayash, thank you so much for sharing your time with us today. And thank you everyone who logged in. I hope you'll be able to join us next week. Finale Doshi Velez and Mason Quartz will be talking about denoising and discretion, AI support for normative decisions. Everyone, have a great day.
Thank you so much.